Okay, so in this video, we're going to be talking about ground and excited state. We already talked a ton about ground state, but we're going to talk a little bit more about that and what the heck does excited state mean. Okay, so here we go. First thing we're going to do is we're going to do something like, let's take a very simple element. Let's take magnesium. Magnesium has 12 electrons. That's what it says. Ground state simply means the electrons fill all the stable energy levels first. So obviously, this is what we do. 12 electrons. 1s2. So we know that 2 of those 12 electrons are in the first shell, which is the most stable shell. 2s2. We know that every energy level or shell starts with an S. That's why the second one. And we still have more electrons to plug in. We've only used 4 of them. And we know in the second shell we can have a max of 8. 2p6. So I've used 10 electrons. First shell filled, second shell filled, third shell. We got 2 electrons left. 3s2. Now, the reason that I put 3s2 in a different color is because that is the valence shell. And that's what we're really concerned with. That's where electrons can make bonds or not. So, we have this. Now, in dash, it's going to be 2 in the first shell, 8 in the second, and 2 in the third. This is ground state. All the electrons have been placed in the orbits, shells, and subshells that are the most stable. Okay? All right. So 282, that is ground state. Now, for the excited state, you have to understand this analogy. If you are standing on the ground floor and you have steps going up to the door of your house, you're most stable when you're standing on the ground floor. This is like these electrons are the most stable because they're at ground state. They're cool. They're not doing anything. But if somebody pokes you hard and you jump, you may jump up to the first step. That's like if I put heat, light, or electricity or an explosion into an atom, it doesn't absorb the explosion or the energy in the neutrons or the protons. It absorbs it in the electrons. Now, to jump up to that step, if you don't have enough energy, you're going to fall back down to ground. Same thing with electrons. Electrons need a specific amount of energy that they have to absorb to move up to the next energy level. If they don't have that specific amount of energy, they will just stay where they are. So, let's take this for example, 2A2. If we put electricity into that magnesium atom at ground state, maybe one of the second shell electrons would gain enough energy and it would look like this. Instead of 282, it would look like 273. So what has happened is one of the electrons has jumped up. Now, that's called the excited state. If you put a lot of energy in there, that may jump way out. And the further out the electron jumps, the more unstable it is. It's like you, when you jump up, either you're climbing a ladder or going up steps, the higher you go, the more unstable you are. So the electrons don't like it out there. Remember, they have to absorb energy to jump up. They don't like it out there because they have too much energy, too much ADD going on. So they're very unstable. They want to jump back. But in order to jump back, they have to give off energy. Then they can jump back and be happy again. Now, the energy is mainly in the form of light energy. So there are 3 names for light energy. Light energy, radiant energy, and the big chemistry term, quantum energy. Quantum energy just means light energy. Now, once the electron jumps back, it gives off light energy. And this light energy can be seen with something called a spectroscope. A spectroscope is kind of like a prism. And I have some examples that actually worked on the video. So, every element, now this is really weird, every element, when you excite it, the electrons jump out, and then when they jump back and give off light. And the cool part is every single element has its own unique set of bright lines. In other words, radiant energy that's given out. So like road flares are made of strontium. When you excite strontium, the electrons jump out, but when they jump back, they give off red light. Okay? Every single element, when you excite it, when the electrons jump back, they give off a specific light, a specific colored light, which is really cool. So, like analogy, fingerprints are to people as the spectral lines are to the elements. You can figure out what element it is by burning it and looking at the electrons when they jump back, what light they give off. I think that's pretty cool. So this is ground state. All the electrons fill the closest orbitals and subshells and shells. And then excited state, you have to excite the electron to make it jump out. It doesn't want to be out there, so it jumps back. Okay? So this is mercury, and I'm zapping it with 10,000 volts of electricity, and as the electrons jump back, you can see two very bright lines, which are called spectral lines. The bright lines are in the area of green and blue. So those bright lines would be for every single mercury atom that's excited and jumps back. That's how you know you have mercury in the compound that you're looking at. The next element is my most favorite to see. This is neon gas, and it's, like I said before, getting hit by 10,000 volts. Look at all the spectral lines on neon gas. Look where they are. So you have Roy G. Biv, and you have ROY, red, orange, and yellow. There's a little bit of G, which means there's a little spectral line of green in there. But for neon, the electrons always jump back down and make spectral lines very brilliant in the red, orange, yellow, and there's one in the green. So that's how you can tell that this element that we have is neon gas. The next element is helium, and look how beautiful the spectral lines are here. You have Roy, R-O-Y, so you have red, orange, and then you kind of skip into the blues. So these are the specific spectral lines that helium electrons give off when they jump back down. And the final element we're going to do is argon, and look at this, just one spectral line in the BIV, blue, indigo, and violet area. This is a very easy one to spot. Argon electrons jumping back. So now the coolest part about spectral lines. How can they be used? Well, how in the world do we know what a star is made of when it's millions and millions and millions of miles away? Easy. Stars give off light. You can look at the light with the spectroscope and see the spectral lines. And whatever the spectral lines are, you can match them with the elements from Earth. So they know exactly what stars are made of. That's so cool. But even more interesting are the meteorites that come from space. This is the largest one found in the United States. And what's so cool about this is they take a hunk of meteorite, they burn it, then they look at it through a spectroscope, and they can see the spectral lines. And the spectral lines for the majority of meteorites give us two elements, iron and nickel. I think that is really pretty neat. But I believe one of the most important applications of finding spectral lines is the application for forensic studies. This is a forensic scientist, and what they do is they find a piece of material at the crime scene, and they have a special instrument that can go right there, burn a little piece of material, and figure out the elements by looking at the spectral lines and matching them with the various elements. It's called a spectrophotometer, and it can also be used at the crime scene to tell the difference between human and animal fluids, which is pretty wild. And the FBI loves this tool because it's also used to figure out what type of elements are in drugs that they find on people or in the house or whatever. So it's good for drug investigations.